Okay, good morning everyone. This is the video about the time series. Last video we saw how we can do the eigenvalue decomposition in order to get the best features, synthetic features derived from the original features that best describe the observation actually. Um, so moving on from the PCA, we go into this new dimension, new style of representing the time series, which is called the piecewise aggregate approximation and symbolic aggregate approximation. In this, we are going to see that how you can make use of a simple way of approximating a time series than the conventional way of using the Fourier transform that is normally used, a very versatile computation technique to approximate any time series in the world whatsoever. But this one is computationally more efficient, faster, and so it's a pretty interesting way of at least for me, that's what I realize of modeling a time series. So what are we going to do discuss in this video is how do we produce approximation of a time series. What are we going to use to approximate a time series? Why are we going to approximate a time series? Why are we going to use those kind of features to approximate time series and not something else, right? So let us get quickly started. Um, First thing what we will do is that we want to see that what benefit or value has our principal component analysis, the principal components brought so far. The only way to know that is by making use of some independent technique by which we can make use of these features before going into further modeling and decision and rule creation. We would like to know whether how good these principal components are representing the time series. To me, this would be an innovative way of trying to verify the principal components against the time series, because just relying on principal components that it gives the variance, so it is good to represent the data. I guess it's not enough. So we need some kind of a concrete evidence to show that those principal components also behave similarly or in the same way how the original time series attributes would behave. So we are going to make use of the principal components, which will become our pseudo timestamp values or synthetic timestamps values, to recreate the time series which we originally crawled from the websites. And then we will try to, once we get those time series, we are going to try to put them back against our hypothesis or what the discoveries that we made during the principal component analysis, whether the time series derived from the principal component for RHB Bank and Sarika Takaful, they bear any similitude. Does that still hold good at that stage, or it is only true while doing the principal component analysis? We are going to similarly test the correlation between the RCE, the other stocks, the RCE Capital, TA Enterprise, and Tune Protect, whether they are still strongly influenced by PC2, but this time in the form of representing it in the form of a time series. And similarly, whether public bank is really unique time series behavior than the rest of the stocks. So that is a new way, new information by which we can take a look at the stocks and their behaviors in a new dimension. That is what we are going to do. This is all the the constants and the constraints that we have set while developing the time series, but I think the best location to discuss them would be the code. So the next video, when I'm going to take a look at the codes, I will share with you these constants and the constraints, how they have been selected and why they have been selected in that way. Okay, just before leaving this concluding this video, I would just like to put a primer on the time series. So time series approximation is basically nothing but, we all have heard about Newton-Raphson method, and the Newton's method, and the mean value theorem and Rolle's theorem, and these theorems that are used to approximate a linear function, right? And then on the other side, we have also seen Taylor approximation or Taylor series expansion, which is a versatile way of performing a nonlinear approximation. Uh, when it comes to a complex combination of function, we make use of Fourier transform to do the approximation, which is an extremely powerful way of doing. It is something that is one of my favorite functions, the Fourier. And uh, but then there comes a new paradigm of trying to represent every time series, which is a combination of many series superimposed on each other, similar to what the Fourier transform does is it decomposes all the different wave functions inside a combined combination of a wave function. So in this case, it before you do symbolically represent a time series, you try to you try to decompose by piecewise approximation. So you break down the time series into small windows of time, and in those windows of time, so you can imagine that you have on x-axis, which is the time scale. On the y-axis you have the values of the time scale, the values that have been measured. So for that window you try to see how many values poll into that window. You take a mean of that. You can take any other measure too, if you would like, but generally in piecewise aggregate approximation you would take the mean in that window, and then all the windows you would then represent with the mean, and you will drop off all the complex fluctuations that you see in the time series. So the time series gets approximated in the piece by the pieces of these mean values of the values of the original time series in a particular window of time. And then you use those piecewise approximation, uh, how many times those kind of approximation the pieces appear in the entire length, say n length of time series, how many times they appear, which will give you the frequency of occurrence. And then you try to find out the equiprobable occurrence of those means, basically the pieces. And once you can get the distribution of how many times it repeats, those pieces repeat, those repetitions and are translated in the form of probability of occurrence in the entire n length of the time series. And by simple symbols like A, B, C, D, E, alphabets, or you can also use 1, 2, 3, 4, but normally A, B, C, D, E, because it is helpful for future computation. And then each piece with a particular probability of occurrence is given a symbol like A. If some other piece with a different mean, with different frequency, will be given a symbol B. And so you represent the whole piecewise aggregated approximated time series now in the just form of symbols which have been derived basis of the probability of the occurrences in the entire window of n time, and that is your, how you say, condensed concise version of approximated time series representation, which is called symbolic aggregate approximation, which is to me a very very interesting and a very very innovative way of representing the time series, with which you can do many beautiful things further. So that's the summary, what the PAA and SAX stands for. In the next video, we will jump into the code, how it is performed actually on the codes. And that is when we will discuss all the details of it. And then later on from the coding, we will come back to the report to see how the plots and the approximation look like, right? So I conclude this video with that. Thank you.